Okay, AP Physics, here's your first little content video over motion diagrams. Some of the stuff you probably already read in the textbook, and I hope that you're doing great with it. You can put this on 2 times speed if you'd like, if you understand what we're going through, but I want to point out some of the main things that I hope that you're getting here. Motion diagrams are a way to simplify the motion of large objects. We eventually will look at large object and how the different parts of it move, but right now we're going to take a large object and turn it into a point mass. So motion is simply the change of an object's position with time. And a motion diagram are snapshots of that motion at equal time intervals. They have to be equal time intervals. So it could be 1 second, 2 seconds between each snapshot or something less. For many types of motion, we can treat the object as if all of the mass were concentrated in a single point. We're treating it as a particle, and we're going to see how that particle moves. And that's how a lot of the physics that we're going to start with acts. We're treating it as a point mass moving through space. So it has no size, no shape. There's no top or bottom to it. It's just a point of mass moving through space. And so here's a motion diagram here. A red arrow is the starting point. 0 is always where we start with our motion diagrams. Hopefully you're labeling your motion diagrams in your packet. And this particular particle is slowing down. And here's a question for you. Describe the motion of this object. I already said it's slowing down. It's traveling a straight line, right? Is there anything else we can say about this? Does it come to rest here? Well, the answer is we don't know from this diagram here. It's slowing down. It could stop here. Maybe it's going to continue that slow speed for a long time. There's not enough information here. So if something stops on a motion diagram, you draw an arrow to it and you label it, it stops. You can put labels on a motion diagram to help describe that motion. Okay, I describe the motion of this object. What's happening here? Well, it starts on the ground and it moves up. Would this be a ball thrown into the air? Think about that for a second. Could this mimic a ball thrown into the air? The answer is no. A ball thrown into the air would start out fast and progressively get slower as it went up. This is progressively getting faster. So what could this mimic? It can't be a free falling object. It has to be something like a rocket or something else like that, accelerating upwards. Okay. What direction is this particle headed? The answer is we don't know because this motion diagram is not labeled. Don't turn in any motion diagrams like this. As soon as I do this, now you know what direction this particle is headed because you know where it started. Okay. A couple physics quantities. You read through this hopefully in your textbook. A vector is any quantity in physics that has a magnitude, which is a size, and a direction. A scalar is any quantity in physics that only has a magnitude. And here's the common ones that we're going to run into. In physics, a scalar would be something like distance. I traveled 59 miles today. A displacement would be a vector. That would be saying I traveled 59 miles, and I traveled 59 miles northeast of Kalispell or something else like that. That would be a vector. It has a magnitude and a direction. A scalar would be something like speed. You look at your speedometer in your car and you say, I'm going 70 miles per hour. Velocity would be that magnitude of the speed, 70 miles per hour, in the westward direction, or a negative 70 miles per hour, which means I'm going left or right. Okay. Acceleration, same thing. It's a vector, has magnitude and direction. Time would be a scalar, mass, energy, and then we'll look at these ones later on in the course. Okay. So let's just look at these guys. Oh, I didn't realize I didn't clear my page here. Give me 1 second here. We can put the same thing together. So adding more information to motion diagrams, this is what you're going to do throughout the rest of your packet. And to do that, we want to say where is it located. And to say where it's located, we're going to have to choose a coordinate system. I'll show you that here in a second. You won't do much of that in your packet. And then when was it there, you're going to label it with a time. And labeling it with a time right now is just going to be you guys labeling 1, 2, 3, 4, and so forth. So let's say we have a slide going down a hill. This is what you had in your little packet, or in your chapter. If we take this sled and we're measuring it over time here, we can plot this to give it more information. Instead of just a motion diagram, we can put an axis on here. And you can choose any axes you want. We can start at the origin here. We can start at the origin here. It doesn't matter. And you'll see why when we start to do math with physics problems, why that doesn't matter. But once we define our axes, every other point's going to be defined based on that. And this would be our point 0 here that we're starting at the top of the hill. And we can define the position here as position x0 the initial x position, and y0, the initial y position. And in this case, it's going to be 0 in the x and 20 in the y. So this would be 0 meters, comma, 20 meters. And this tells us where that sled is located to start out. We continue to go down to 1. This would be x1, y1, 2, x2, y2, 3, x3, y3. And you can see for our motion diagram, the time between each interval is 1 second. So 1 second elapses here, then 2, then 3, and we're at t equals 3 seconds. So now we're being more descriptive. We have a location with a coordinate system. We define an origin, and we have a time label for when we got there. And we're getting more and more descriptive with our labels here. Now, before we move any farther here, I want to help with some coordinate systems here. When we look at angles in physics, if you draw a regular axis system, this is our x-axis, and this is our positive x-axis going to the right here. We always define this as 0 degrees for angle measurements. And then everything going this direction is a positive angle measurement. So something like this might be a positive 60 degrees. And going this direction, we have a negative angle measurement. So if we had a negative 50 degrees, we would label it like this. If I want to get over here, I might be at 130 degrees or something else like that. And it could be positive. Or I could get there by going a negative in the x direction all the way around 180 plus to get to that same position, another 50 or something else like that, okay? So that's how we label angles in physics. So you're going to see on these diagrams here, we have a 45-degree angle here, and it's measured from our x-axis upwards. This is a position vector, and that position can be described with coordinates, like 15 meters, comma 15 meters, or it can be described by a vector, R3 being for 0.3, and this little arrow above it means that it's a vector. It has a magnitude and direction. The magnitude is 21. That's the length of this vector to get from here to here. It's not 15 or 15. If we draw this equilateral, this right triangle, and we solve for the hypotenuse, it's 21 meters. And that's our length. And then our direction would be 45 degrees measured from the x-axis. And that's where a little measurement here comes in handy. Okay, there's other ways to write this vector as well. Every time you write a vector, always draw it with an arrow. Some books will bold or italicize the vector. We can't write bold or italics with our pen or pencil, so we always write an arrow above it. So if I want this to be a vector, I can write it like this, where I give the magnitude and then the direction. You should write this in your notes. A vector, a general way of writing it is the magnitude. It's always magnitude first, comma, then the direction. Sometimes that direction is given by 45 degrees north of east, and you give a little bit of extra information. If we already have an established axis system, they can just give you an angle, and we know the angle is always measured from our positive x-axis, just like we have shown here. Another way to write a vector is this. We can take our r vector. Oops, I don't know why this isn't working very well. We can take our r vector, and we can write it like this. I can say r3 equals, and we put it in kind of triangular brackets like this. Instead of parentheses, smooth parentheses, which would be for a coordinate label, for a vector, use triangular brackets, and we can put 15 meters, comma 15 meters. The only difference here are the brackets, and if you see these brackets as a physicist, you know this is not just a coordinate, this is a displacement vector to get to the point x equals 15 and y equals 15. And you can draw that vector on a diagram. That's different than just giving a point in space. Okay. The other way you can do this is r3 and our vector equals 15 meters in the I hat direction, which this is a vector called the unit vector. And we'll talk more about that in the future. But 15 meters in the I hat direction plus 15 meters in the j hat direction. And this is the unit vector in the y direction. And we'll talk more about that when we talk more about vectors. But that's kind of your overview of how we write vectors. Okay. Okay, vectors, let's make sure we didn't miss anything here, represented by arrows. We've got that with our arrow here, and when you write it out, you write the arrow above it. The length of the arrow is proportional to the magnitude of the vector. And so this vector is 21 meters long. If I write one that's 42 meters, it's going to be twice as long on my page. Okay? And the direction of the arrow represents the direction of the quantity measured. And so we write it the direction that it's supposed to go. Now I've got another one written right here. It's 21. It's in black. Going this direction is 45. These two vectors are the exact same vector. The position of that vector, where it starts, does not matter. Why do I say that? Well, if I just gave you this part that's circled in red, and I gave you that on a page with no origin, you would know that the length of this vector is 20 meters, the angle is 45 from the positive x-axis. You would be able to define your origin wherever you want, and you could still use this vector to solve a physics problem. And you'll see why when we start using vectors. But here's what I want you to understand right now. A magnitude and a direction is all you need. You do not need the coordinate system. All you need is a magnitude and direction to define a vector, which means that vector can be the same length and same direction, and it could be written like this. All of these vectors are equivalent. Maybe they're all 21 long, and they're all at a 45-degree angle. Every single one of these vectors is the same vector. It doesn't matter where it's positioned. All vector is a length or a magnitude, which is the length, and a direction, which is the angle. It doesn't tell you where to put it, okay? Direction and magnitude. If I take a vector, vector A, and I say 2 times vector A, I don't change its direction. Maybe it's at 45 degrees. It stays at 45 degrees. All I do is multiply the magnitude of that vector by 2. So I'm going to get twice as long. If it was 21 meters here, now it's 42 meters. And I draw a vector that's twice as long. If I put a negative in front of it, it stays the same length. So this is negative A. So it's still 21 meters. It's still at the same angle here, 45 degrees. And I'm going in the opposite direction now. I've just started here and now I'm going this direction. And this one you could redefine as a different angle. So our angle is defined from the x-axis. This might be an angle better defined like this, where we have a negative angle, or a positive angle that goes all the way around from this side. Okay, but if you put negative in front of it, it just switches the direction. Distance. If we measure distance, distance is the length of the actual path taken by an object. So let's say an object travels from A to B along this path. If you just took a little wheel and ran that wheel, keeping track of your distance the whole way, that would be your distance measurement, which is a scalar. It's just a measurement with a magnitude. So it's just 20 meters. And we usually represent that with S. Okay. How we show a change in position is something called displacement. That's a vector. And so a vector is going to be from A to B. We draw our arrow, and then we have an angle here. So we'd say 20 meters from A to B with 25-degree angle. Now, these aren't very good diagrams because there's no way that this distance is 20 meters and the direct route is also 20 meters. If this was 20 meters for a direct route, this would have to be something less, maybe like 12 meters or something like that. But you get the idea. The displacement is from A to B. It doesn't matter how we got there. All it is what is the distance between A and B? How far did I go to get there directly? And what's the angle from A to B? And we're going to use displacement most frequently in physics, and it's a vector. Okay. To continue with displacement, we're going to use R to represent displacement. Hopefully you read that in your chapter. R is the displacement vector, and displacement is the distance between our 2 dots on our little motion diagrams. Now these are your position vectors. Position vector R3 and R4 goes to point 3 and point 4, and it's the arrow from the origin to your point, and it has a magnitude and a direction. The displacement vector is this. This is how your book defines it, but I like to solve this equation to say this. Your change in position, your displacement vector, is equal to, in this case, we'd subtract R3. So it'd be the vector R4 minus the vector R3. The position vector at time 4, that's this guy, this length right here, minus the position vector at time 3 gives us this length right here. And in general, you can write this, displacement, the displacement vector is equal to the position vector at your final position minus the position vector at your initial position. Here's my final position. This will be final. Here's my initial position. And if I subtract those two, I get my displacement vector. So that begs the question, how do we add and subtract vectors? Because somehow I have to take this arrow, and it turns into this arrow. If I take R4 minus R3, I have to get this distance between these two, and I have to get this correct angle going down on my page from these 2 arrows. How do we do that? And this will become really important for us when we start looking at velocity and acceleration. Some of you might already be there in your packets. I'll make a video for you for that part of your packet on Thursday, and you'll be able to look at me walking you through that as well. But adding and subtracting vectors becomes really important in physics. So here's how we do it. Vector addition. If you want to take vector B and add it to vector A, you always do it like this. It does not matter which one you start with. You can start with A or B. It doesn't matter. You're going to get the same answer. Here they started with A. They draw vector A. Once you draw one vector, you take your other vector and you place the tail of it at the tip of the first vector. So the tip of A gets the tail of B. You draw B at the same length and at the same angle, and then you connect the two. So from my starting point at the tail of A to the ending point at the tip of B, that is my addition of those two. A plus B equals this vector right here. And that's how I get a magnitude, a distance, and an angle, because I have to connect those two at the right angle when I add vectors. Now, if you want to try that, go ahead and try it for these two vectors. What is P plus Q? And you can pause the video if you want to. P plus Q, I'm going to start with Q here. So if I draw Q, I'm going to go to the end of Q, and now I need to draw P. So P is going to be coming off like this. I'll try to draw it about the same length. Maybe it's something like this. And now I'm going to go from the end of Q to the end of P, and maybe it looks like this. That looks most like A to me. Is that our correct answer? Yep, that's our correct answer. Here it is, P plus Q. They did it the other order. They did P first and then Q, and they get the same answer, an arrow going down. Look at what I did. I did Q first and then P. So I go this direction, and I get this one. And they go this direction, and they get the same thing. It doesn't matter which way you do it. You get the same answer. If I go Q plus P on this one, I'll get the same little arrow there. Okay. Vector subtraction. Here's how you subtract vectors. I have A and B again. If I want to subtract them, this is what you have to do. Subtract B from A. That means I want to take A minus B. Here's how you do it. You cannot subtract vectors in physics. That doesn't work. We only add vectors. So how do I add vectors? Well, I do this. I say A plus negative B. And we already talked about this. We know how to take the negative B vector. The negative B vector is just this guy flipped over. So I'm going to write my negative B like this. It's just this arrow going this way. And this is negative B. And now I can add the two. How do I add? I don't need this anymore. I draw my first one, and then I draw my second one, going off the end of the first one, and I connect them. So that's what they do. They draw A first, and then my negative B written right here is drawn next. And then A minus B is going to be the result of that. Okay, see if you can do that with these guys, P and Q. P minus Q. I want negative Q. So let's flip this over. It's going to be that direction. There's my negative Q. Which one do you want to draw first? It doesn't matter. So I'm going to take my P. Let's draw our negative Q on my P. There's my negative Q. And let's connect them. There it is. P minus Q is this vector right here. And that looks most like D. Is that our correct answer? There you go. There's our D. P minus Q. And we get our D. I hope that helps with some motion diagram questions. I'm sure you have other questions. Please email me with them, and I will post more content videos in the days to come.